Okay, so today's notes, we're going to do the background to undetermined coefficients, which I said is also called the Annihilator approach. You need to know both of those terms. So this is one method for solving non-homogeneous linear differential equations. Section 4.6 is another method. You will need to know both, and you will need to know them by name. What we are learning today, we learned in section 4.1. I told you you're going to need this later, and then we kind of didn't look at it again. We looked at something like this. dy dx is equal to dy. D is called a differential operator. D is really telling you to take the derivative with respect to x. So this is saying differentiate y with respect to x. So a differential operator transforms a differentiable function into a new function. So for example, if I apply the differential operator to ae to the bx, so that's saying differentiate with respect to x, we would get a b e to the bx. Okay, one thing that's important for us to know is that differential operators possess linearity. Here's what I mean by that. If I apply the differential operator to a fx add b gx, that's the same as applying the differential operator to f of x multiplying by a, and then applying the differential operator to g of x and multiplying by b. Okay, first example. If we have this, I want to write that in terms of a differential operator. So this is saying take the derivative of y with respect to x, and then take the derivative again with respect to x. Another way to write that is d squared y. So take the derivative with respect to x twice. So this then, that's an n, can be written this way. Now, you're not just going to see d as a differential operator. You might see d add 3, d squared minus 4d, etc. These are all linear differential operators. Okay, when we first introduced differential operators, besides looking at what they were, we also looked at writing an equation in terms of a differential operator. So we also need to be able to do that. So any linear differential equation can be written in terms of d. For example, let's say we have a y double prime plus b y prime plus c y equals g of x. This first term is d squared y, bringing the a out in front. So taking the second derivative of y with respect to x. This is b dy. So differentiate y with respect to x. This is cy. So on the left side, what we can do is factor out everything that's not a y. So this is ad squared plus bd plus c times y equals g of x. All that stuff in parentheses, that is a differential operator. So another way to write this if we let L be equal to all that stuff in red I circled, that AD squared plus BD plus C, then what we get is L applied to Y is equal to G of X. L is called a second order differential operator. If we look at the following example, y double prime plus y prime plus y is equal to 3x. We need to be able to write this in terms of differential operators. To get y double prime, I apply d squared to y. Y prime is just d. That's a 1. Times y is equal to 3x. Okay, any questions so far? No. Okay, we are going to need to use these differential operators when we're solving non-homogeneous linear differential equations. One thing that's important to note is that an nth order differential operator factors as long as the auxiliary equation, or the characteristic equation from yesterday, factors. Okay, so the auxiliary equation for this one, again, you're going to treat it like it's homogeneous, so ignore the 3x, is m squared plus m plus 1. This doesn't factor, hence that differential operator will not factor. Okay. These differential operators lead us to what's called the annihilator operator. Bless you. Okay, if L is a linear differential operator such that when I apply L to Y, I get 0, we say that L is an annihilator of Y. Here are some examples. If I apply d to a constant, so I have a constant and I take the derivative with respect to x, I'm going to get 0. If I have x and I apply d squared, so I take the derivative twice with respect to x, I'm going to get 0. What about x squared? How many times would you have to take the derivative in order to get 0? 3, right? So d cubed. So then this d squared, this d cubed is called the annihilator for x squared. It annihilates x squared. Okay, so that helps us with polynomials. For polynomials, what we just saw is that d to the n will annihilate x squared, all the way up to x to what power? N minus 1. Therefore, to annihilate a polynomial of degree n minus 1, you will use d to the n. Okay. Next example. We have 6x to the 5th minus 40x to the 4th plus 31x. What differential operator will annihilate the entire expression? What? D to the 6th. So the d to the 6th will annihilate each of those factors, or each term. Okay, that's just for polynomials. So then the question arises, what happens if you don't have a polynomial? If you have an exponential, if you have sine, if you have cosine, something like that. So that's what we're going to look at next. Here's what I mean by exponentials. Let's say you have e to the alpha x, or xe to the alpha x, all the way up to x to the n minus 1, e to the alpha x. Do you remember from yesterday why that x would be there? Very good. A root that's repeated. So if you just have these two, it means the root is repeated once, or the root happens twice. Okay, so to annihilate, here's what you're going to use. The quantity d minus alpha to the power n. Okay, n is the number of times the root is repeated. You will need to memorize these annihilators. So for polynomial, it's not difficult to memorize, but for the exponential, you need to memorize that. Okay, e to the 6x. What would we use to annihilate that? D minus 6. Okay, I also want us to show that that is in fact the correct annihilator. So we will apply d minus 6 to e to the 6x. What you're going to do is you're going to distribute. So you get d e to the 6x minus 6e to the 6x. So this means take the derivative with respect to x. So we get 6e to the 6x minus 6e to the 6x, which does in fact give us 0. Hence, that is the correct annihilator. Questions so far? No. Okay. What if we have 4e to the 3x plus 2x e to the 3x? In that case, what are we going to use as our annihilator? D minus 3 squared. So the 3 comes from that exponent. The squared comes from the fact that the root is repeated twice. That 4 and that 2 we don't care about. Those don't have anything to do with our annihilator. Okay, this one we are also going to verify that it's the correct annihilator. So we're applying d minus 3 squared to 4e to the 3x plus 2xe to the 3x. Any ideas? What does your intuition tell you to do? I heard somebody say something correct having to do with the annihilator. You're going to have to multiply it out. So you get d squared minus 6d plus 9. You're applying all of that to 4e to the 3x plus 2xe to the 3x. Okay, so then d squared is applied to 4e to the 3x. It's also applied to that 2xe to the 3x. 6d is applied to both. And then we have 9 multiplied by both. So here, the first derivative will be 12e to the 3x. So the second derivative then is 36e to the 3x. This one, you'll have to do the product rule. So I'm going to do that first up here. This will be 2e to the 3x plus 6xe to the 3x. Now, that's the first derivative of this expression. We have to take the derivative again. So when we do that, we're going to get 6e to the 3x from that first term. Second term, we're going to have to do product rule on again. So we get 6e to the 3x plus 18xe to the 3x. So this now takes care of those first two. Here, we take the first derivative and multiply by negative 6. So the first derivative will be 12e to the 3x multiplied by negative 6 is negative 72e to the 3x. Here, I'm taking the first derivative and multiplying by negative 6. I have the first derivative here, so multiply by negative 6. And then these two just multiply by that 9. Okay. So now we have to see what cancels out. We have 36e to the 3x, 36e to the 3x, negative 72. We have 6, 6, and negative 12e to the 3x, 18x, 18x, negative 36. So hence we get a 0. Okay, so not too bad, just tedious. Be careful if you make a small mistake. You're toast for the rest of the problem. Okay. Any questions before we get to the last kind of differential operator? Okay. What else did I mention that we're going to need to be able to annihilate that we have not seen yet? Sine and cosine. Okay. Do you remember from yesterday that when we were solving the homogeneous linear differential equations, and you got complex roots, that your solution involved sine and cosine? Your solution involved sine and cosine, but it also had e to the alpha t. So it had e to the alpha t for the real part, and then your imaginary part was cosine of beta t plus sine of beta t, but you had c1 and c2. Okay. So the last kind has a bunch of different possibilities that you could see. You could see e to the alpha x cosine of beta x, e to the alpha x sine of beta x. If there's repeated roots, so if those complex roots repeat themselves, you could have e to the alpha x cosine of beta x, x e to the alpha x sine of beta x. And those repeating roots could keep going. If they repeat n times, then you'll have x to the n minus 1, e to the alpha x cosine of beta x, x to the n minus 1, e to the alpha x sine of beta x. Okay, this one gets a little more complicated. Any combination of sine and cosine, you're going to use the following. The quantity d squared minus 2 alpha d, add the quantity alpha squared plus beta squared, all to the power n. N would be for the number of times that the root repeats itself. So let's say we're looking at the following expression. E to the negative x cosine of 2x plus e to the negative x sine of 2x. To use this differential operator, we need to identify alpha, beta, and n. What is alpha in this case? -1. What is beta? 2. Does the root repeat itself? How do you know if the root repeats? Because some people are going to say yes because there's two terms. Right, there's got to be an x out in front, like an x or an x squared or something, so the root does not repeat itself. So then we'll use d squared minus 2 alpha. Alpha is -1 though. So plus 2d plus alpha squared plus beta squared. 1 plus 4 is 5 to the first power. Okay. I'm not going to have us verify because I think you can do that on your own. Any questions before we talk about the last idea with annihilators? Okay. Here's the last thing that you need to know, and then we'll do 2 examples with it. The product of annihilators L1, L2 will annihilate the sum of y equals c1 y1 plus c2 y2, etc. So if you are annihilating a sum, and let's say each term has its own annihilator, you multiply them all together, and that will annihilate the entire sum. Okay, example 7. We have 7 minus x, add 6 sine of 3x. Okay, you should be able to tell you can't pick one annihilator for the entire sum. What will annihilate those 2 terms? D squared. This will be what we just did above. In this case, what is alpha? 0. Beta is 3. So you're going to have d squared. That is just 0, so now we're here. Beta squared is 9. So we have d squared plus 9. So then, for the whole sum, you're going to use d squared multiplied by d squared plus 9. Okay, last example. E to the negative 5x, add 6x squared minus 5 plus x e to the x. Okay, I want you to take a minute or two and find the entire annihilator. When you're ready, talk to someone next to you and see if you agree. Okay. Let's look up here and see how we did. You should have needed an annihilator for the first term, for the next two terms, and for the last term. Annihilator for the first term should be d plus 5. The next two terms is d cubed. Last term is d minus 1 squared. That x denotes a repeated root. Now, why do we not see e to the x in this expression? If the root is repeated, there's two terms that have it. We have e to the x and we have x e to the x. Why do we not see e to the x? Do you remember yesterday how they both got their own constants? C1 e to the x plus C2 x e to the x? C1 must have been 0. So that's why we don't see that one. So don't get confused just because you don't see e to the x. That x denotes that it's repeated.